All right, so for section 3.3, we're going to cover 5 different topics. We're going to talk about the general shape of a graph, and we're going to kind of sort of carry this through for several chapters. But in this particular case, we're going to talk about skewness. We're going to standardize things into z-scores. We're going to explore Chebyshev's theorem, the empirical rule, and how to detect outliers. So I'm going to actually show you the textbook. I know it's kind of weird. All right, so what I want to look at is these 4 histograms that we've got. Pardon me while I play with this mess. There we go. All right, so we've got 4 histograms. So I've got this one, and this one, and this one, and this one, the 4 histograms. Basically, if something is skewed, you want to look at the tail. Where's the tail? So on this one, the tail is on the left. The smaller values are on the left. So this is skewed to the left, which means it's going to have a negative skew. Okay, this is skewed right. He'll have a positive skew. This one is perfectly symmetrical. It doesn't have tails either on the left or the right. So this skewness is 0. It's not to the left or to the right. There's just no skewness. Okay, this one is very skewed to the right. Okay, this one's got a nice long right-hand sided tail. So you're going to have a positive right-hand skewness. So when we refer to the skew, look for the tail. Okay, where's the tail? If it's on the left, it's negative. If it's on the right, it's positive. And we're going to use this, especially this cool little shape right here. This is going to keep popping up throughout the course. So the next thing that we want to look at is a z-score. So if you think about it, if we talk about the means and the medians and the ranges and interquartile ranges, all this kind of stuff, that's going to be different for every single scenario that we have. So it's going to be a whole lot easier if we standardize. Okay, so what we're looking at is we want the mean to be 0, or the median to be 0, sorry. That's going to be where the bulk of our data is. Sorry, my dog just attacked my cat, so I got distracted. Sorry. Anyway, so first of all, how do we figure out a z-score? So we've got a method for this. And for any particular z-score that we want, so we just say z sub I, okay, the formula that we use is the particular x value that we're looking at minus the mean, okay, so minus bar x, divided by the sample standard deviation. Okay, so notice we're dealing with samples here. So let's give it an idea of what this is. Okay, for our previous example, I kept that here. That is the wrong screen. Okay, I kept that here. And so I just kept up the 6 data points, and then we've got a sample standard deviation of 4.335897. So if I wanted to standardize this, okay, if I wanted to standardize it, let's just grab 12. Okay, I want a z-score for the data point of 12. So my z-score for the data point of 12 is going to follow this thing. So my z-score is going to be the data point, which is 12, minus the mean, which was 16. We found that out in the last section, divided by the sample standard deviation, which is 5897. So what we get there is, I've lost my calculator, we'll have a negative z-score, because 12 minus 16 is negative. So 12 minus 16 is negative 4. Okay, divide that by 4.335897, and I'm going to get a z-score of negative 0.922253, blah, blah, blah. Okay, so in this case, that thing's z-score is going to be negative 0.923. We'll just keep it at 3 decimal places from now on, just to make it easier. So this would be a 6. Okay. So just for ease, the homework may tell you different decimal place values, like 3 or 4. For our computations from here on out, I'm just going to use 3 decimal places. So what does that mean? That means that this value of 12, it gave me a negative. It's to the left of the mean. Okay. So my mean was 16. Well, 12 is to the left of 16 if you think about a number line. Okay, so I take that 12 and I standardize it into a z-value, or a z-score, of negative 0.923. Now, I'm going to show you something else in the book, because it kind of sort of helps you see what we're doing. Because I could do this for all 6 data points, but it gets kind of globby. All right, so here's what we've got. Different data. But we found out that the mean in this thing was 44. We've got data points at 32, 42, 2 data points at 46, and 1 data point at 54. Once those things were standardized, okay, we found out that our mean was 0. And anything to the left of the mean took on a negative value that got further away from 0. Anything to the right of the mean took on a positive value going away from 0. And now what we want to look at is, what do those z-scores mean? Okay, so if you have a z-score of 1, that means 1 standard deviation. Okay, so this is almost 1 standard deviation away from what we were looking at. So let's think about that for a second. If the mean was 16 and I'm referring to a data point of 12, okay, my standard deviation was 4.336. So I'm getting pretty dang close, because this is 4 units away. Okay, so what we're doing is we're converting this. So my z-score is going to tell me how many standard deviations away I am from the mean. Now, we have a mean of 0, so that's a tick mark, that's not a 1. Okay, so I can go 1 standard deviation this way. So this is going to be 1 standard deviation. This is going to be 2 standard deviations. This is going to be 3 standard deviations. This is just going to be my little cross point, okay? I can have -1 standard deviation, -2, and -3, okay? So what did we say earlier? And this is where I'm going to formalize. So I'm going a little bit out of order. I'm going to skip from z-scores to the empirical rule, okay? And then I'm going to come back to Chebyshev's theorem. A z-score is going to tell you how close, how many standard deviations your data point is away from the mean. Okay, so again, mine is to the left because it's negative. 12 is to the left of 16. And it's almost 1 standard deviation away. Okay, so when I look at that, here's what I find out. This is the empirical rule. Okay, between when I say 1 standard deviation away, I mean either to the left or to the right. Okay, it's not cumulative. In other words, this is not 2 standard deviations. If I say within 1 standard deviation, that means to the left or to the right. To the left or to the right. Okay, so I realize if you look at this as a number line, that this is 1 unit, 2 units. I'm not referring to 2 standard deviations. If I say 1 standard deviation, it means I can either go right or go left from the mean. Okay, 2 standard deviations means I would go 1, 2, or I would go 1, 2. 3 standard deviations is 1, 2, 3, 1, 2, 3. Okay, so here's what the empirical rule says. The empirical rule says approximately 68% of your data will lie within 1 standard deviation of the mean. So again, think about that. That means 1 to the right and 1 to the left. So 68% of my data will be in this area here. Okay, that's 1 standard deviation. Okay, if I look at 2 standard deviations, about 95% of all of my data will be within 2 standard deviations. So again, I'm not saying just this unit here because that contains 2. I'm saying 2 to the right or 2 to the left. Okay, so in reality, it's a width of 4 units. Okay, so about 95% of my data will lie within 2 standard deviations. So most of my information should lie within this interval right here. Now, what we have at the end is 99.5, which our book refers to as most. Okay, most of the data will lie within 3 standard deviations of the mean. So 3 to the right, 3 to the left. That should encompass all of your data. So that's going to refer now to outliers. So here's what I've gone over so far. We've done the shape as far as what skewness means. We know how to take a z-score. What it's going to do is take it out of all of these different scenarios we can standardize. where our mean will be 0. Okay, our mean will be 0, and then our z-score will tell us how close we are to the mean, measuring within standard deviations. We did the empirical rule, which is these percentages down here. And now we're going to talk about detecting outliers for a second, and then we'll come back to Chebyshev's theorem. All right, detecting outliers, if we're using the empirical rule, if you have more than 3 standard deviations to the right or more than 3 standard deviations to the left, we consider those outliers. Okay, so if we have a data point that lies way over here, okay, so looking to the left on my screen, my data points went from all the way from 10 to 21. Well, what if I had a data point of 87? Okay, that's not going to be in this area. That's going to be way over here to the right. Okay, that's going to have a monstrous positive z-score that's more than 3. Okay, he's an outlier. Why on God's green earth is there an 87 in mixed up with the 10s, 12s, 16s, 17s, 20s, and 21s? Okay, so that could be students' ages in my, I don't know, in my class of some sort. Well, then all of a sudden I've got an 87-year-old. Okay, so that's what we're doing. Now, another method, and we're going to look at Chebyshev's theorem. So Chebyshev's theorem simply is another perspective on this. So the process is once you have determined your z-score, okay, once you have determined your z-score, you can use that information. So my z-score was this, okay? I can use that and apply it into Chebyshev's theorem, and that's going to tell me what percentage of the data must lie in there. So it's not going to be as broad as just saying 1 standard deviation is 68%, 2 standard deviations is 95%, and 3 standard deviations is most. Okay, we're going to get a little bit more specific here. So let's throw in the z-score that I found a while ago using my data point of 12. Okay, so if I throw that in here, what that looks like is 1 minus 1 over negative, and remember I'm going to go to three decimal places at this point. So I've got 1 minus, so 1 minus 1 divided by, and I'm going to do negative 0.923, and I'm going to square that. Okay, so I just squared the denominator. Okay, so what I have is, holy cow, I typed that in wrong. I was like, that is so dead wrong. 1 minus 1 over, and I've got negative 0.923. That is so different. All right, squared. And grab that, and there we go. Okay, so what I have then is my z-score, I squared it, I divided it into 1, and this is going to tell me that 17% of my data should lie in that area. Okay, so think about it this way. From 12 to the left should account for 17% of my data. From 12 to the left should account for 17% of my data. That's essentially what we're doing there. So that tells you about the 5 things that we're doing. Now we got one more thing about detecting outliers. There's another method that we can use for detecting outliers. Okay, and I am getting this because I'm kind of sort of running short on time, but here we go. All right, I could have a lower limit, okay, of, what I'm going to do is take quartile 1, not quadrant 1, quartile 1, which is your 25th percentile, okay, and I'm going to subtract 1.5 times the inner quartile range, okay, that number will be your lower limit. So let's say I got a number of 8, okay, anything to the left of 8 is considered an outlier based on my data. And I'm just kind of sort of making stuff up here. Your upper limit, okay, is going to be Q3, so your 3rd quartile, and I'm going to take plus 1.5 times that number that you got for your interquartile range. Okay, so it's a whole lot easier and more straightforward to just use your z-scores. If you get a z-score bigger than 3 or to the left of -3, we consider it an outlier. We got to explore it a little bit more. You can also use these for a little bit more particular. You can use this as well. You can use one or the other, anything like that. But those are your processes. So that is section 3.3, and I'll see you for 3.4.